This video is all about using differential equations to model real-life situations. We've already done some work on this previously in regular maths and in mechanics, and all the mechanics problems you looked at were all similar to this, where if we know the displacement is given by x, we know that the velocity is the rate of change of x with respect to time, and we know the acceleration can be thought of the rate of change of the velocity with respect to time, or the second derivative of the displacement with respect to time. Now we're going to see a problem with further maths integration techniques to solve something like this to begin with. Then we're going to see a second example that's quite a lot harder, but also a very, very common exam question. So we'll start off with the simple example, and then we will save the more complicated one for a minute. So we are told that a particle P is moving along a straight line at time t seconds. The acceleration is given by a equals t plus 3 over t v. Given that the particle is at rest when t equals 2, show that the velocity is given by v equals ct cubed minus t squared, where c is a constant to be found. So we want an expression for v here. We've been given an expression for the acceleration. We know the acceleration is the same thing as the rate of change of the velocity. So that allows me to rewrite that equation like this. So just swapping the a for a dv by dt. So I've got this first order differential equation that I want to solve to get an equation for v. Now this is pretty similar to the general form of a first order differential equation we saw previously, where v is taking the place of the y and t is taking the place of the x. And so because of that, I'd like to move the 3 over tv to the left hand side, so that I've got the v here and the v here on the same side of the equation, like we do when we have the y and the y here. So moving that over to the left hand side gives this equation here. So we can see that this is the equivalent of my dy by dx. The 3 over t, or rather the minus 3 over t, is the equivalent of my p function. The v is my y and the t is the equivalent of my q function. So we're going to use an integrating factor to solve this. The integrating factor is going to be e to the power of the integral of this. So that's what I've got over here. When I integrate this, I get minus 3 ln t. Move the minus 3 up here to be a power, so that the e and the ln cancel out. And so I find then that my integrating factor is just t to the minus 3. So multiplying through by t to the minus 3, I'll get t to the minus 3 dv by dt, minus 3 t to the minus 4, so obviously the minus 1 power here and the minus 3 power here would make a minus 4 power. And then on the right hand side, the t times the t to the minus 3 would make t to the minus 2. Remembering that we can rewrite this left hand side as just being the derivative of v times the integrating factor. When you differentiate this with the product rule, you get this. Equal to that on the right hand side. And then I can integrate both sides with respect to t. So integrating this side with respect to t will just give the inside. Raise the power, divide by the new power, plus a constant. I've used the letter d here to represent my constant, just to show that I know it's not going to be the same as the c here. So that's why I've called it d, just to avoid myself getting confused. I'm now going to substitute a boundary condition in to try and figure out what that constant there is. Now notice here it said, given that the particle is at rest when t equals 2. At rest, that means it's not moving, so the velocity is 0. So the velocity is 0 when t is 2. So if I substitute that in down here, so the velocity is 0 when t equals 2. So v is 0 here, will mean that's the left hand side is 0. T is 2, oops. So 2 to the minus 1 is a half, so I've got minus a half here, plus d. Therefore I can see here that d has to be plus 1/2. So if I then make d a half here, and all I'm going to do to finish this problem off, just to make this a bit simpler, is multiply through by t cubed. If I multiply this side by t cubed, I just get v. Over here, t to the minus 1 times t cubed will be t squared, with that minus in front. And a half times t cubed will be a half t cubed. And this is in this form, and I found that c is a half. So that's a relatively simple problem, because they told me the equation at the beginning, and all I had to do was change the a to be a dv by dt. So that was quite nice. Now we're going to see in this next example, we've got a lot of text, a lot of information that we need to deal with. So let's read this through. A storage tank initially, so at the beginning, contains 1,000 litres of pure water. Liquid is removed at a constant rate of 30 litres per hour, and a chemical solution is added at a rate of 40 litres per hour. The chemical solution contains 4 grams of copper sulfate per litre of water. Given that there are X grams of copper sulfate in the tank after T hours, and assuming that the copper sulfate immediately disperses throughout the tank on entry, show that the equation can be modelled by the equation dx by dt is equal to 160 minus 3x over 100 plus t. And then we've got a couple of other questions we need to answer as well here. But let's just focus on that part A first of all. So dx by dt, this is the rate of change of the amount of copper sulfate. That's because x is the amount of copper sulfate in the tank, so this is the rate of change of the copper sulfate in the tank. Now I know that there's copper sulfate solution going in, and I know that there's copper sulfate solution going out. The copper sulfate solution going in was 4 grams of copper sulfate per litre. So there was 4 grams of copper sulfate per litre going in, and I know that there was 40 litres going in per hour. So if there's 4 grams in every litre, and there's 40 litres going in every hour, then 4 times 40 is 160. So I know there's 160 grams of copper sulfate going into the tank per hour. Going out, well, I'm not sure about how much copper sulfate there is per litre going out of the tank at the moment. It didn't tell me that in the question, but it did tell me that there was 30 litres per hour going out. So if I can figure out the concentration of the copper sulfate that's going out of the container, I can do something similar to what I did here. Now, the key assumption here in this question is the fact that the copper sulfate immediately disperses throughout the tank on entry. That is crucial, because what that means is that the concentration is constant throughout the whole tank. So that means that there's no difference between the concentration of the copper sulfate at the top of the tank compared to the bottom, or in the middle. So if I've got a load of copper sulfate coming out the bottom of my tank here, that's going to be exactly the same, the concentration of the copper sulfate coming out of the tank down here, will be exactly the same as the concentration of the copper sulfate there or anywhere within the tank, because it's immediately dispersed and mixed throughout the tank. So that's really helpful, because if I can work out the general concentration of the copper sulfate in the tank, then that will be the same as the concentration of the copper sulfate that is leaving the tank. So let's think about that then. Let's think about the concentration of the copper sulfate in the whole tank. Well, I know that there's X grams of copper sulfate in the tank. It told me that in the question. Where was it? Given that there are X grams of copper sulfate in the tank. So the concentration would be X divided by how much there is, the total volume of liquid. So let's now think about the total volume of liquid in the tank. Well, I know there was 1,000 litres to begin with, and I know that there was 40 litres added per hour, and I know that 30 litres were removed every hour. So that means 10 litres of liquid is being added to the volume every hour. So after 1 hour, 10 litres, after 2 hours, 20 litres, after T hours, 10 T litres. So T hours later, there'll be the initial 1,000 litres that there were at the beginning, plus 10 times however many hours have passed. So that means then that the concentration in the tank will be X divided by all of this. So this is the concentration of the copper sulfate throughout the tank. Therefore, it is also the concentration of the copper sulfate that is leaving the tank. Therefore, if I've got 30 litres of that leaving every hour, then I've got 30 lots of that grams leaving per hour. Just in the same way as when I had 4 grams of copper sulfate per litre going into the tank and 40 litres going into the tank, so 4 times 40 was 160 grams of copper sulfate going into the tank per hour. Similar idea here. Multiplying these two things together will give me the concentration of copper sulfate leaving the tank every hour. The amount of grams leaving the leaving the tank every hour. So I've got this equation, and I can just do a bit of simplification here. I can divide through by 10, cancel, cancel, cancel. And then this equation now we can see is actually the equation I was asked to show. There we go. That was the equation I was asked to show, and we have done just that. So that's part A of the question. That's the really difficult thing to do in this question, I think. And I hope that this process here makes sense, because this is the key thing. And then using that assumption to figure out that the concentration in the whole tank will be the same as the concentration leaving the tank. Right, part B. Hence, find the number of grams of copper sulfate in the tank. So we after 6 hours. So we want to solve this differential equation and substitute 6 into it, basically. So I'm first going to move this x function over to the left-hand side, so it looks like this. So this is now in a form where we can use an integrating factor, because this is the equivalent of my p function. So integrating factor will be e to the integral of this, which basically then gives this. Move the 3 up here to be a power. Multiply through by 100 plus t all cubed. So we know the left hand side will give me this. The right hand side will be 160 times the integrating factor. Integrate both sides with respect to, there's a mistake there, that should be a dt. Yeah, integrate both sides with respect to t. We get that. I'm now going to use my boundary condition. Now I know obviously at the beginning the tank had, it was pure water at the beginning. Pure water at the beginning. So therefore the amount of copper sulfate in the tank at the beginning is 0. So substituting 0 and 0 in here, we get all of that 0 equals 40 times 100 to the power 4. And so rearrange and I find that C is minus 4 times 10 to the power 9. So we know C now. Now we can actually work out what the concentration, how many grams there would be in the tank after 6 hours by substituting 6 in here and here. And doing that and rearranging, we find that there were 882 grams to 3 significant figures. Final part of the question. Explain how the model could be refined. So this is a reference to the fact that we had this assumption here, and this key assumption where we said the moment copper sulfate is added at the top of the tank, it's immediately spread throughout the whole tank, which is a bit unrealistic really. So if we were to refine this model, we'd want to try and find a way of appreciating the fact that there's the concentration of the copper sulfate is not going to be constant throughout. It's going to take some time for the copper sulfate to disperse throughout the whole tank. To begin with, the concentration of copper sulfate at the top of the tank is going to be much higher than at the bottom, assuming of course that the copper sulfate is being added at the top and leaving at the bottom. But hopefully that makes sense, what I'm saying there. So how would we refine the model? Well, we would just want to take into account the fact that the copper sulfate will not immediately disperse when entering the tank. Actually doing that, actually refining the model to do that would be quite complicated, and do ask me about that if you're interested in that. We don't need to go into any more detail other than saying that that's how we would improve this model.